Hello everyone, welcome to this introductory course on machine learning. Before we get started with machine learning specifically, let's talk a little about data science in general. What the objectives are, how do we do it, and what are the challenges involved. Then we can talk specifically about machine learning and talk about some of the core ideas that differentiate machine learning from, say, classical statistics. I should caution you that the overlap amongst the various fields of data science, you call it machine learning, data mining, statistics, etc., are quite significant. There is a large overlap. However, there are some core ideas that differentiate machine learning from the other areas like statistics, and we'll talk about those as well. So let's talk about data science to begin with. So data science is all about learning from data. How do you learn about the world we live in using data we've observed from the world? So the starting point for all of these data science techniques is observations from the real world that we called data. Observations from the real world that are very precise are usually given the term data. So whenever I say data, I mean observations from the real world in very precise terms. So the data could be a tabulated list of numbers. It could be pictures, it could be videos, it could be a recording of voice. All of these are data, particularly because they're very precise observations. Agree? So if we start from precise observations or data, and we finish with a summary of what we understand about the world, that analysis techniques, all the analysis techniques that go into that framework, where we start from data, let's draw a tabular list of data points. It could be tabular, it could be a tabulated list, it could be images, it could be anything, as long as it's precise. And we finish with some kind of a summary of how we believe the world works like from this data. Then the analysis, all the analysis that goes from here to there is what we would call data science. So let's write data on one end, and let's say a mathematical summary. By summary, we mean if I describe to you how the world works like, that's a summary. However, if I describe to you how the world works like in very, very precise terms, we call it a mathematical summary or a mathematical model. Math model. So a math model could be as simple as y equals some a plus bx, a linear model, where we say as x changes, this is how I believe y will change. To put some context to this, let's say this was your GPA, your grade point average, or how well you did your exam scores, and this is the annual salary that a graduating class actually makes. So this is the first column records their performance in a course, in a program, and the second column records their starting annual salaries. Let's say if we had data of this kind, I'm making this data up obviously, if we have data of this kind and we say GPA on the x-axis and annual salary on the y-axis, and we plot out these points. Let's say I plot these points this way, some points like this, and we draw a straight line that runs through these, something like that. It could be a straight line, it could be something else, but let's say we had something like that, and we said, y equals, or let's say salary equals a plus some b times GPA, right? This is our summary of how the world works like. And this is what we call a mathematical model. So the mathematical model that we are about to embark on doesn't have to be as simple, doesn't have to be this complicated even. It could be as simple as average salaries or so and so. Any specific summary of how we believe the world works like, starting from data, is what we will call a mathematical model. So all the kinds of tools that go into this arrow here is what we would call data science. It could be statistics, where we do assume that this data was generated by something like a linear model, and their entire job is to find A and B. It could be data mining or machine learning, where we might try to automate all of this, and we don't try and assume anything specific about the data, where the data came from. So let's talk about all of that in a minute. So to summarize, data science is all about answering this question of, can we learn about the world around us starting from data? So we would do this by largely 3 steps. Take data as input, that includes collection of data, cleaning of data, etc. Find a pattern in the data, which is what we do as data analysis, or of looking for a linear pattern or looking for more complicated patterns. Maybe the data is much more complicated, so we will be looking for more complicated patterns. And more importantly, the final output, which is to summarize the pattern in a mathematically precise way. Summarizing the pattern in a mathematically precise way. Moving on to machine learning specifically, the machine learning phrase revolves around the process of automating this entire procedure. So that's at the core of all of this, right? Can we automate this model building? So this is a model, mathematical model. Can we automate this model building? So when we start with that, the first thing to ask ourselves is, what's the challenge? Why is this difficult? If we can answer this question of why this is difficult, then we can start to gain some insight into the various aspects of machine learning. So let's begin with that. So I'd like to start with, let's say data was without noise, very precise. There is no noise to it. Then the data might look something like this, right? So, the data might look as a specific pattern. If data looked like this, then finding a pattern is extremely simple for us. We look at it and say, hey, a straight line fits this wonderfully well. We're done. So we don't need anything more to understand or summarize data into a mathematically precise way. But unfortunately, data usually doesn't look this way. Data usually contains both information and noise. Information and noise. And this poses the largest challenge for machine learners, statisticians, data miners, call them what you will, but this is the major challenge. How do we take data, identify information, and throw away noise and capture this information into what we would call a mathematical model? And this splitting of data into these 2 parts is at the heart of almost everything we do in data science. If we can do this very well, we're pretty much done. So to appreciate this a little more, let's take a quick look at, let me just put something together. Let me, let's say we had data. Again, a 2-dimensional simple list. Let's call it, again, as we said, let's call it a GPA versus salary. And we had data, right? Now, machine learning usually does not assume that this data comes from a specific kind of mathematical model. Statistics, on the other hand, usually says, okay, I'm going to make an assumption to begin with. I'm going to assume that all of this data came from, let's say, a linear model, or logistic, some nonlinear model, or exponential model, or quadratic model, a specific model. Let's assume that. And if I do assume that this data came from, let's say, a linear model, then the question boils down to very simply finding the intercept and the slope, and that's it. 2 parameters for the linear model. However, machine learning tries to stay away from making that assumption. Machine learning says, I'm going to try various different models to separate information from noise, and I'm going to evaluate each of those models to find out which of those, either quadratic or, linear or log normal, whatever model you're going to choose. I'm going to try each of these models and try to find out which does better. And to be able to do better and to be able to evaluate and compare various kinds of models on the same data set is at the heart of what differentiates machine learning from standard statistical or statistical inference techniques. So to do that, the big first step that machine learning does is to take all of your data and split them into two different sets. All of this data, split them into two different sets. The first set we would call the training set, and the second set we'll call the testing set. Now, if you get into more and more complicated machine learning techniques, you will see that people start splitting it into more than two groups. They might have a training set, a validation set, and a testing set, or even sometimes more complicated than that, they might have 4 different sets. They might call one the holdout set and so on. However, the base idea, the core idea, is very well illustrated by just using two. For most cases, 2 different sets, the training set and testing set are okay. So there are various ways to split the data into 2 different sets. The most popular and the usual way that is considered very good is to just randomly throw them into 2 different sets, and people follow different kinds of rules. 70-30, 70% goes into training and 30% goes into testing, and subtle differences of those exist. But let's say randomly we start throwing things into the training set. For example, everything in red goes into the testing set, let's say, and everything in the green probably blue in this case, goes into the training set. So we might split. So all of blue goes into training, and all of red goes into testing. We just arbitrarily, of course, I'm assuming this is not, this is just GPA and salary, for example. It's not time series data. It's just data measured at one point in time for all students. Now, that being said, what we might do is we might start with the training data. We might plot the training data, something like that. We might plot the training data, and we might ask ourselves, let's do some, okay, we might plot the training data and say, I'm going to fit a model. It might be the linear model, it might be other models. I'm going to fit a model for this. The issue is that all of these models some models are very complicated, some models are not that complicated. So for example, if I fit polynomial model of very high orders, then I could get an extremely good fit. So this is just my training data. I'm looking for the best model. What I could end up doing is I could end up fitting a polynomial model that looks like this. Oh, sorry. That looks like that. So yeah, of course it can't go back. It's it's got to have one-to-one relationship. My drawing is not that great, but let me try that again. So this might be my training data. Of course, I'm taking advantage of the fact that I'm drawing rather than actually using actual data. So this might be my training data. So as you can see, if I simply use training data and try various different models on it, then almost always I will find that the best or the best model turns out to be the most complicated model, which manages to fit all of the data precisely. Now what I've done here is essentially chosen the most complicated model that unfortunately ends up fitting both information and noise. The problem with this is that if I look at the testing data, which is data that I might not have seen or is going to be data in the future, could be, then information by definition is consistent, is structured, is a pattern, and therefore going to repeat itself. But unfortunately, noise, by definition of what noise is unstructured, random, and will not repeat itself. And therefore, if I use this specific green model in the future on testing data, let's say, then the noise is not going to fall along this curve, and I ended up, while I wanted to only capture information, I ended up capturing information plus noise. So if I do plot the testing data, it might look something like that. So all of my testing data will be completely off. While my training data told me that I perfectly explained the data, my testing data tells me that my predictions are really bad because I ended up fitting the noise in the training data. And this green line is classically what we will call overfitting, because the fit that we came up with overfit the data, meaning it fit information and it fit the noise. On the other hand, if we have a very simple model, a model that just says, the y-axis, the salary is equal to some constant, that's a very simple model, that might look something like this. That might look something like that. That's a very simple model, where it says salary is just salary, is just something like some $60,000 or something like that, and this is GPA. So while we would call this an overfit model, because it fit noise as well, we will call this an underfit model, where it did not manage to capture even, or it managed to leave out even some of the information. So overfitting ends up fitting information and noise, and underfitting doesn't manage to capture even all the information that was available to us. So the idea is to strike a balance between the two by using the training set and fitting something, in this case probably something that could I'll put another training point here that makes this look a little better. So the red line is a linear line, obviously in this case. Maybe that's a good balance between overfitting and underfitting. By that I mean it manages to capture as much as information as is possible from that given data set and leave out noise. The good part about doing that is that if we go back to training versus testing, now this is information plus noise. This is also information plus noise, right? It's all data. Now the idea here is, if I manage to create a model that only captures the information. See, information is something that's consistent. So this information is the same as this information. They are the same. But noise, they are not the same, right? They're not the same. This noise is different. It's random, the definition of noise. This noise is different from that noise. So if I do manage to capture, if I overfit and capture information plus noise, that wouldn't do well, because the information would match but the noise wouldn't. If I underfit and only capture a little bit of that information, that'll do okay, but it'll not do as well because it didn't capture as much information. But if I do manage to capture a model, write down a model that contains all the information, then the best part of the story is that if I take this model, which does okay on the training data, not as good as the overfit model, because the overfit model will do extremely well on the training data, but our measure of success shouldn't be on the training data. Our measure of success should be fitting a model here, taking that model and testing it out here. If I do that, an overfit model will perform badly on the testing data because it doesn't fit noise. An underfit model will also perform badly in the testing data because it didn't manage to capture all the information. But a model that strikes a good balance between overfitting and underfitting will actually do extremely well in our testing data. Right? That's the idea. So what the machine learning folks do is they start trying a sequence of models. Let's try. Machine learning folks tried a sequence of model complexity. Right? More as I go to the right, this is a very abstract picture I'm going to draw. As I go to the right, the model complexity increases. Now, prediction error. Now, what happens? Now, let's just talk about the training data. What do you expect? For models that are extremely less complex, like the straight line here, agreed? Or, our prediction error will be very high. As I get more and more a complex model, like this green line here, my prediction model will go down. But in sample or training data, this is how it will look like. The more complex a model, the better I would be able to capture information and noise and explain everything away. However, this is not our measure of success. If prediction error was our measure of success, we will go for the most complex model. Our measure of success is going to be on testing data. So as I keep going to the right, my testing data starts to capture more and more and more and more information. And therefore, my performance on testing data starts to increase. Something like that. But then at some point, the model becomes so complex that it manages to start capturing noise. And therefore, once you start capturing noise, your performance on testing data decreases because the testing data has noise that's very different from the training data, because that's again the definition of noise. If it was the same, then it would be called information, and therefore on testing data this happens in testing data. And then the machine learning techniques identify the minimum or the best and call this the best model. So machine learning, at the heart of it, is focused on automating this model building process, and it realizes that the more complex a model, the better the fit is for data in general, and therefore it says, okay, let's split it into training versus test and start building models on the training data and evaluating in the testing data, and therefore we should be able to nail down on the model that's the best in terms of predicting on data that it's not yet seen out of sample data, or otherwise to say, if this model ends up capturing more of the information, leaving out noise, right? That's at the heart of all of this. Now, to summarize all of this, the easiest way to think about data in general is to think of this as information plus noise, and any process of analysis trying to capture information and leave out noise. The challenge is always this identifying the split, because we are only given this data which comprises both together. Now, it might not be a specific addition. I'm just showing it plus here as a metaphor, but it could be any kind of complicated relationship between information and noise, but that's fine. It contains both information and noise. Machine learning tries to automate it, as I said, and one of the techniques it uses in this automation is this train versus testing split. Now, we've talked about underfitting and overfitting. This slide summarizes all of what we talked about. Now, having differentiated machine learning to a certain extent, again, it's not a crystal clear difference between machine learning and, let's say, statistics. There is a bunch of overlap. Very many techniques, including things like logistic regression, were ported from the statistics toolkit to the machine learning toolkit. And of course, it's being used by machine learners quite a bit, even though it originated long ago when computers didn't exist, from the statistics community. It can be ported, the overlap is high. Irrespective, machine learning tools tend to be slightly different, at least in the way they are implemented, or at least in the way they start with in terms of assumptions, right? Based on the assumptions they start with. Now, to dig a little more into what we might see in machine learning as we go forward, it's a good point. It's a good idea to start classifying the various tools that machine learning has up its sleeve. And a very good way to start this characterization or classification, characterization of all the tools is to think of two different categories, one called supervised learning and the second one called unsupervised learning. So if you look at all the tools in machine learning, they can almost be aggregated into these two broad groups. There are some other variants of it, like semi-supervised learning and things like that, variants of this. However, largely, supervised learning and unsupervised learning are easy way to classify all the tools that we have in machine learning. Now let's talk about what these are. So when we look at data, as I showed you, the GPA versus salary data, GPA versus salary. Now, you might have other things like GPA, you might have age, you might have GPA in different subjects as different columns. The data could be more complicated. However, in this simple example, where this is your average GPA over all courses, I guess, and salary, what we might ask ourselves is, can GPAs predict salary? In which case, we call this the independent variable, and we call the dependent variable. We could have more independent variables, like GPAs of different subjects, right? Now, when we have an input, this is what we'll call, we could have GPAs of different subjects in different columns, right? And then we could have salaries. When we have these inputs and we have an output, a desired output, and our objective is to find the relationship between these inputs and these outputs, inputs. In this case, just one output. When our entire objective is to find the relationship between the two, critically, there is an output. Then we call it supervised. The supervised comes from the fact that we do have a desired output, so there is some kind of supervision on how good or bad our analysis or model is. Every time we come up with a model, that predicts the salary, we can actually go back to the exact salary that was recorded in our data and compare our predicted salary against with the desired salary and evaluate how good or bad our model is, and that's where the word supervised comes from. Now, you might have examples where you don't have a desired output. For example, let's say you're looking at what people did on the internet, right? What did they like a specific product? Did they navigate to a different web page? Various attributes, their age, their location, how long they were on the web, etc., etc. Lots and lots of characteristics about a person, let's say, who comes to your web page or who comes to your retail store. Just lots of characteristics, right? You don't have a specific desired output, but of all the customers who walked into your retail store, can I look at my entire customer base, and create segments of these customer base so that I can target my ads in the future towards certain customer bases, right? So this is called market segmentation, and it happens over and over and over again because people would like to understand their market, and the best way to understand their clients or the market is to group them into 3 or 4 or 5 groups and understand what makes each group distinct from another, and that way we understand our customer base. Rather than understanding every one of our 10,000 customers, we can understand how these 5 groups behave or how many people are in each of those 5 groups, etc. So this is called market segmentation. Here the key is that there is no output. There is no column called dependent variable or desired output. We simply have a set of columns, and we like to group all these rows into 5 or 6 different groups, and in those cases we call it unsupervised learning, right? And the tools that allow us to do supervised learning are very different from the tools that allow us to do unsupervised learning, and this is kind of obvious from the way it's structured. Supervised learning gives us a desired output that allows us to precisely evaluate how good or bad our algorithm is. However, in unsupervised learning, you have no such ability to evaluate how good or bad our algorithm is, and therefore this poses an interesting challenge on how do you compare models against one another. Here, comparing models against one another is much easier because we can rely on something like our prediction error, right? This prediction error is specifically something that is very relevant to supervised learning, where we can go back, compare the desired output to the actually recorded output on the testing data and come up with the testing data or the training data to come up with prediction errors. So in terms of examples, let's going back to the slides. So supervised learning is all about building a mathematical model using both inputs and desired outputs. That's the key. These desired outputs are sometimes called the ground truth. You have those. For unsupervised learning, you don't have the ground truth, meaning you don't have the true segmentations of how you don't have the true customer segmentations for you to compare against. Right? So for example, the examples I've shown you here, again, I showed you tabular examples, but data doesn't have to be tabular. For example, you might have a problem where you say, I've got a whole bunch of pictures and I want to come up with an algorithm that looks at these pictures and says whether there is a horse or a cat or some particular object in the picture or not. So what I might start with, a training data set, which contains lots and lots of images, those being the inputs, and for each image I have a binary number that says either there was a horse or not, 1 or 0, and inputs are images and desired outputs are the 1s and 0s. I give all of this to the training algorithm and ask it to train itself in its ability to identify a horse in a picture or not. And because I have these labeled, horse or not, each picture, I would call it supervised learning. Now, semi-supervised learning is something that people, is a little softer than supervised learning, where I might say, hey, I have 1,000,000 images, but of all those 1,000,000 images, only 100,000 of those, I have them labeled as horse and no horse. The other 90%, I don't have them labeled, but they are available. But still supervised, because our objective is still to match a desired output, but the key is that only some of these have labels. So we call them semi-supervised learning, but that's a very special variant of supervised learning. Determining if a client will default to return a loan. If somebody asks me for a loan, can I essentially say, predict whether the client will default or not? Again, you have a desired output from historical data on who all defaulted and who all did not default. And if a call center employee will quit, again, you have from historical data whether employees quit or did not quit. So we can differentiate this from unsupervised learning, where we go in and say, so unsupervised learning, where we say we have inputs, but we have no desired output. So in such cases, our objective is to find structure in the data, like grouping or clustering. Again, going back to the market segmentation example, it's easier to relate to. So as I already mentioned, since we have no labels, it's a challenge to evaluate model performance in unsupervised learning. Now, to finish with this, let me summarize a little more of what could be going on in these. So amongst supervised learning and unsupervised learning, if we further dig in, you can further classify some of these techniques that go into supervised learning into two categories. So all the techniques that go into supervised learning, you can further classify them into either regression or classification. Remember, supervised learning always has a column that calls itself desired output or output in general. Right? So when this desired output is a continuous number, is a number, any number, like I'm trying to predict the temperatures in my city, the temperature could be any number. It doesn't have to be 1 or 0. It doesn't have to be 1, 2, or 3. It could be any number. It could be 67.1342. It could be 67.1345. Any number, a continuous number. Then we call it regression in general. Linear regression is a special case of regression. So whenever we have the desired output being a continuous number, like a real number, we call it regression. However, when our output is a classification, default or no default, somebody will quit or not, they belong to a customer category A, B, C, or D. There are only 4 quantities, A, B, C, or D. There are 4 customer categories, and I'm taking every customer and classifying them into either A, B, C, or D. So whenever my desired output is a category of a certain number, 4 categories, 10 categories, whatever, they're not continuous, then we call it classification. We classify each row into a category. In regression, for each row, we make a predicted number. That's supervised learning for us. For unsupervised learning, again, this is the case where we do not have a desired output, in which case we could dig in a little more and say, hey, we can further classify the techniques that go into unsupervised learning into clustering, where given a set of rows, we'd like to group them. Clustering is just another word for grouping. You group them into clusters, and each group contains people who are very similar to one another. Then we have dimensional reduction. This is generally compressing data. All the way from, if I take an image and compress that into a smaller file, what am I trying to do? I'm trying to reduce the size of the file while I make sure I do not throw away important information. So the idea again is to throw away data, but not the information. Of course, the information looks different in this case, but not throw away the information. That way, compressing is essentially throwing out the data and keeping the information, and then using only the information to reconstruct the image, right? And we might do this in finance. For example, I might have a large table of different returns from different stocks, and I might want to create portfolios that do not contain all the stocks, and therefore I might compress this stock market data, and I might do dimensionality reduction. In that case, we specifically try and call it factor analysis, but we try to use that to find out what is the essence of the stock market, what is the information that I can distill from the stock market so that I can actually, let's say, create a tracking portfolio or things like that, right? So, and then we have these association rules, and you have to be careful here. Association rules can be used for both unsupervised learning and actually supervised learning, but largely their history traces from being used for unsupervised learning, though people can use it for supervised learning too. So association rules are like, I give you what people have done. So people have walked into a supermarket, for example, that's the classical example, and for every, the columns are different products that the supermarket carries, and the rows are different customers, and customer who bought X always bought Y. Something like that. If somebody bought X, they did buy Y. Can I deduce? Can I infer that? So of course it doesn't have to be true for every pair of X and Y, but then can I search for those unique X and Ys for which I can actually say with high confidence that people who always bought X did end up buying Y. And remember here again, Y was not dictated to us to begin with. All the columns were given to us, and we are looking for patterns for like if X then Y. Again, X doesn't have to be one product, it could be a sequence of products. So X could contain two products, and then we can say if product A, B, and C, then Y. Something like that. So since Y was not given to us before we started the problem, we were just given this table and said, look for patterns of this kind. We call it unsupervised learning. But you can easily imagine where you have a different objective in a supermarket where, for example, the Y column actually reads people who paid by check or people who paid by credit card. Then we could say, hey, that is our desired output or the desired interest to analyze. So can I say if people bought X, Y, and Z, then they usually paid by check. And if people bought A, B, and D, then people paid by a credit card, something like that. So the moment we have a target desired output that we are trying to do with the same kind of if-then analysis, then we could be calling it supervised learning. But again, for historical purposes, particularly in the case of market basket analysis, the so-called where the retail stores checkout baskets are given to us as various columns where we are looking for association rules, we simply say it's an unsupervised learning mechanism, though it can be used for supervised learning in different contexts. So thank you. I will finish with this, and this introductory lecture is all about an introduction to machine learning, specifically trying to gain insights into the core ideas in machine learning that allows us to differentiate machine learning from other areas like statistics, other data science techniques like areas like statistics, and then also talk about the various classifications of tools that go into machine learning and further classifications of supervised and unsupervised learning techniques. Thank you, everyone.